Hurricanes, earthquakes, tornadoes. These words strike fear into the hearts of many, and rightfully so. Natural disasters eradicate houses and entire towns, and there's no way to stop them. Survivors of these events are left without power, meaning there's no way to call for help or to notify loved ones of their safety. To combat this, the Center for Agile and Interconnected Microgrids has created an unmanned ground vehicle designed to traverse treacherous terrain and establish electrical microgrids for temporary power supply. This vehicle uses cameras, LiDAR, and radar to locate a connection port and then establish a connection. The problem lies in the means of connection. The current design uses a robotic arm. This solution produces unreliable results, and the cost of investment to improve the robotic arm would be too large. Thus, Team 17 was asked to design a connector and coupling actuator for mobile electrical grids. Team 17 consists of Trevor Barrett, Nathan Bondi, Sam Krusinski, Travis Moon, and our primary advisor is Dr. Cameron Hadden. Our solution incorporates an electrical linear actuator, a variety of components designed to correct any misalignment in the connection process, and a locking system intended to keep a successful connection intact despite sudden external forces. The connection process can be seen here. Once the plug is fully inserted, the solenoids close, locking the plug in place with two half-circle locking rings. The spring-loaded balls decompress as the actuator pulls away, and the vehicle is now free to drive off, leaving the plug and wire in the connection port. To disconnect, the process simply reverses. Attached to the actuator is the mechanism used to insert and remove the plug. This device is designed to rotate to ensure that the plug can be angled properly for insertion. On the back are three spring-loaded balls that firmly hold the plug in place. These balls are designed to decompress when the actuator pulls away from a locked plug, freeing the plug from the actuating system. The port side of the system is also designed with the intent of guiding the plug in place despite any misalignment. The base of the port is attached to the vehicle, and a platform holding the solenoid and other electronics sits on top. This platform is attached in such a way that it can be angled to assist a misaligned plug. The plug itself is made of 4 copper rings for AC and DC connections, 2 plastic tips at each end, and a polyurethane middle. The wires travel through the first plastic tip, through the rubber section, and finally through the second tip before terminating at the copper rings. A medium-hard polyurethane was chosen to be used in the plug because it is flexible enough to aid in properly aligning the plug when necessary, but is stiff enough to support the weight of the rest of the plug. Our team is suggesting these next steps for this project: build a physical prototype, test it, redesign as necessary, integrate the cable system, and finally verify the control system. To conclude, our team would like to thank these individuals for their help: Ryan Madsen, Dr. Wayne Weaver, Dr. Cameron Hadden, and John Naglick.